got right behind it.
Oh, pens. There's one purple pen here. Hold on. Any second.
Just say, take your time.
Right.
I'm gonna make my itinerary for
I feel like you're always doing something other than.
Bro, is he for real when he's like, this is gonna be terrible?
This is?
I don't know,
The
but I'm
the
gonna
last time I went and talked to him, I think it was last Tuesday before his or last Monday. I said, "How's the internet?" I don't know. He's like, "It's gonna be bad. It's like nothing I haven't seen before."
Well,
I was
he
like,
just said it's gonna be horrible.
I know.
it's gonna be rough. That's what legit his verbiage. Rough.
Okay.
I'm just not thinking now.
Okay, on the screen is a representation of hemoglobin. That is an X-ray crystal structure. What we do for these things is, this is particularly difficult with proteins because they don't want to turn into crystals. We force them with lots of gentle coaxing to crystallize. Once it's a crystal, we can bombard it with X-rays and then look at the diffraction pattern and have a computer figure out what the relationship between all the atoms are. And then with a little bit of computing power, quite a lot, we can figure out which is part of the protein, which is part of the active center, and where the metals are. And with clever stuff like atomic radius, we can predict what oxidation state those metals are in. That's a bit of a reach, because for most metalloproteins, you can't get a good enough crystal structure, and they throw fake atoms into the computer simulation to make the other atoms congregate to fit the data. So it's a little bit of a stretch. So hemoglobin is an oxygen transport protein. It belongs, in general, to the class of molecules called metalloproteins because it has 4 subunits, which are like horseshoes, and I'm not even going to attempt to draw this properly. And somewhere in here, you have 4 metal centers. And we saw on Tuesday that each of those metal centers is called a heme, and it is a porphyrin plus an iron 2+. We know it's an iron 2 because we can measure its redox potential. Iron 2 has a very achievable reduction oxidation potential that is, under the right conditions, reversible. Under the wrong conditions, irreversible. Goes to the iron. Iron 3. The wrong conditions being too much oxygen. So this big subgroup is allowing oxygen to get to the metal, but not allowing too much. And we know that our porphyrin, I drew the structure on Tuesday. What I'm going to do is just call it this. It's supported by the nitrogen from histidine. And we also showed you what histidine was on Tuesday. Histidine has an imidazole side group and that has a pyrrole-like nitrogen that is not involved here, and a pyridine-like nitrogen that is, because that pyridine is soft, as are these nitrogens, well, the two of them, because I have the two pyrroles that deprotonate, the two pyridine-like, and then this gets to be an iron 2 plus in the middle. That gives me, with all this protection around, an open surface. And an oxygen comes and binds to that ion. Hemoglobin, Hb, plus O2 makes this HbO2. Oxygen bound to the ion. Unbound hemoglobin, deoxygenated hemoglobin, is blue. You see that in your veins. That's venous blood. And arterial blood, blood that has been oxygenated, is red. Difference in color. Oh, here's a throwback. A shift from blue to red.
Oh crap. Oh, the question.
I get to use the word twice in the same year. Twice in the same calendar year for a word that doesn't come around but once a decade. A shift from blue to red.
Trichromic.
No,
Diochromic. Something like that.
it's got chromic in it.
Bichromic.
Which one of these two has the shortest wavelength? Blue or red?
Red.
Shortest wavelength, people. Blue or red? Which one of those is the higher energy, blue or red?
Blue.
Oh, we don't know.
What is red?
Blue, it's right here. Blue
Rainbow.
has a higher concentration.
Rainbow, yes?
Yeah.
What is below red in the rainbow?
Infrared.
What is above violet in the rainbow? Violet, above it. More than violet. Ultraviolet. Which one of those two radiations is dangerous?
Ultraviolet.
So what does that tell you about the energy of the wave?
There's higher energy.
This one is higher energy.
What the?
Okay. If that is high energy, tell me about its wavelength.
Shorter wavelength. Oh, I messed that up.
So the shift from blue to red is what? Is a shift to longer wavelength, and that's called a, come on people,
I don't know what I wrote dichromic, but it's not.
it could be hypso,
But it's
Or is
not.
it diet?
or it could be bathy.
That's it.
Bathy.
That it.
Okay.
I'm gonna fix that right now. How do you spell that?
Bathychromic.
What did you
Chromic. Bathychromic.
Dichromic.
Isochromic and bathychromic shifts. All right. What could be responsible for the change in color? All right. It's not the protein. It's the iron. In combination with the porphyrin. Oh, we didn't tell you. Porphyrins on their own, they might be potent. Charge transfer. It's lots of conjugated electron transfer right there. And yeah, porphyrins tend to be, you can make them be nice different colors by feeding electron donating groups in or electron withdrawing groups out. You can actually change the color of the ring. But this might be kind of purplish, and iron, we know iron is red, right? It's that brick red color that we see in minerals. That's iron right there. So this is red, and that is blue. The question is this a change in oxidation state? Is this a change in oxidation state from iron 2 to iron 3? Because I'm adding an oxygen. It could be. It's not. If we take this out of the protein and look closely at what happens, those porphyrins dimerize those oxygens. You make mu. Mu means bridging. Peroxy bridge. So, and you oxidize up to iron 3. Because peroxides are O2 2 minus. So what's going on is this oxygen is being a ligand. It's using a lone pair of electrons, but it has to be in a pocket. The protein is there to protect it from being next to other stuff. So when we first started, this is probably before I was born, when we first started looking at these iron porphyrins to see what the nature of the oxygen bond is, we now know it looks like this. They get destroyed. If you take an individual metallocenter out of the protein and try to make it do its reaction on its own, typically they don't work. And we have things called holoprotein and I can't remember what the other one is. The protein has a role, and it's to protect this iron away from electrons that it doesn't need and binding that it doesn't need. Okay, so they effectively dimerized. This is a really clever piece of chemistry that Max Perutz did. Max Perutz was at the Cavendish lab in Cambridge, and he attached long, stringy groups to the porphyrin. He called that a picket fence. And now, anything that wants to bind to that oxygen that would damage this center is now too far away. It's just pure sterics. And that's when we realized, oh, the oxygen is not bound side on. The oxygen is not bound, I mean, because we'd seen this. I mean, we'd seen A to 2 bonding before. There's a double bond between those oxygens. It could have been bonding through the pi bond. You see it bonding end on. That's Max Perutz. Max Perutz has Max Perutz was at the Cavendish when Crick and Watson stole the data to solve the DNA riddle, and he was not pleased. So he's got a footnote in history. Okay, so we know that once it gets to iron 3, it stops working. It stops working altogether. So this is iron 2. The active site is iron 2, not iron 3. And here's the clever part. This one is drawn upside down from mine, but I'll see if I can kind of just basically reiterate what this sketch is on the board. So on the left, I have the deoxygenated form. There's my iron. Here's the porphyrin ring. That's my histidine. And then basically up here is just protein. Here's an oxygen, O2, dioxygen. And it is about to approach that iron. And when it does, and it binds, that iron 2 plus does not change to iron 3, because iron 3 doesn't do this chemistry. It changes spin. And we have the difference between low spin and high spin. And this iron is now completely in the plane of the planar porphyrin ring. Here's my oxygen bound to it. When it is unbound, that iron sits a little bit above the ring. The deoxygenated is high spin, 55 picometers above the ring. The oxygenated version is low spin, and sits in the plane.
Deoxygenated between which is unbalanced.
That goes here.